Okay, to obtain the dynamic estimation algorithm, now we can go one step at a time, and first, having the estimated state at time k, we'll use it to obtain the predicted state. And this is obtained by applying on the state equation the operator of expectation conditioned on z super k. So this is again information prior to time k plus 1, expected value given z super k of xk plus 1, and xk plus 1 is to be replaced now by the dynamic equation. That's fkxk plus gkuk plus vk. We'll use now the whiteness and zero mean property of the process noise. The fk being deterministic, expectation passes after the f, so will be an fk x hat kk, because e of xk given z super k is x hat kk. This is completely deterministic, so it appears as is, gkuk, and the expected value of vk is 0 because it's white, and the vk noise appears after all the previous vk's up to k minus 1, of which it is independent, have been realized, and the w measurement noises up to k also are there in the system in this zk, and they are also independent. So you can see how the zero mean and independence of the two sequences, measurement and observation noises, comes into the picture. So x hat k plus 1k is fk x hat kk plus gkuk. Now we're interested, a second step, to find the covariance associated with this predicted state, or one-step prediction. To this end, we will subtract the state estimate from the two-state. So here we have the two-state dynamic equation, here's the state estimate. So x tilde k plus 1k is xk plus 1 minus x hat k plus 1k. You have an fkxk minus fkx hat kk, that is an fkx tilde kk. The gkuk cancels, and we have a vk here. So there are two terms left. The known input cancels out, obviously. It is used, but has no contribution to the covariance, because all it does is shifts the mean by a known quantity. Now, the state prediction covariance based on the previous derivation, there was an fk x tilde kk plus vk, the whole thing multiplied by its own transpose. There are two terms. The result will be not four terms, because two cancel out, the cross terms cancel out due to the expectation. So fk e x tilde kk x tilde transpose fk transpose. And again, we pass the expectation past any deterministic quantity. And the second is in the reverse order with transposition, because it was a transposed here. This transposition caused a reversal of this, the order of these two terms. And there's an evk vk prime that gives a qk. There's an fk pkk fk prime. The sum of these two terms is pk plus 1k. And again, the cross terms are 0 due to the fact that vk is zero mean and white, and therefore it is orthogonal on x tilde kk. Remember, x tilde kk contains observations up to time k and process noises up to time k minus 1, because this is how x tilde k was created. Now, having done the predicted state and the covariance of the predicted state, we need a predicted measurement. It will follow in a similar manner by taking the expected value of the measurement equation. So E of zk plus 1 given z super k is E of hk plus 1, that's deterministic, xk plus 1 plus wk plus 1 given z super k. The mean of w is 0, E goes past the h, so z hat k plus 1k, again this k plus 1 is the time argument, this conditioning argument here says up to what point we have the information, is hk plus 1 x hat k plus 1k. So now you can see how the predicted state enters in a nice linear manner into the predicted measurement. Next, we are interested in the measurement prediction error. Before we calculate the covariance, we need the prediction error for the measurement. Z tilde k plus 1 given k is z at k plus 1 minus z hat k plus 1 given k. So we have the actual measurement equation minus the predicted measurement equation. You can see hk plus 1 factors out. Xk plus 1 minus x hat k plus 1k gives you x tilde k plus 1k, and there is a measurement noise here. So this is now our measurement prediction error, which multiplied with its own transpose and taking the expectation will give us the measurement prediction covariance. And again, two terms give us not 4 but 2. There's the 1 with itself, transpose h, the x tilde k plus 1k times x tilde k plus 1k transpose. Expected value is pk plus 1k. There's an x h k plus 1 at the end, transpose, plus e of w, w transpose, that's r k plus 1. So now we have the covariance of the measurement prediction or measurement prediction error. Another term we will need for the calculation of the filter gain was what used to be the static pxz, now in the dynamic case is the expected value of x tilde k plus 1k, z tilde k plus 1k transpose given z super k. Here is the x tilde k plus 1k. H x tilde k plus 1k plus w is the z tilde k plus 1. Again, this w and this x tilde are orthogonal because they are independent, and this has zero mean. Therefore, what we have now is just a single term. Second, because of the transposition, we switch the orders, so this immediately multiplies this, and we have pk plus 1k, the expected value of x tilde k plus 1k, x tilde k plus 1k transpose, and then post-multiplied by hk plus 1 with the transposition. So the filter gain, now this is the pxz, this is the pzz inverse. wk plus 1 is pk plus 1k, hk plus 1 prime, sk plus 1 inverse. With this, we can write the update equation for the state estimate, which yields the updated state estimate, namely x hat k plus 1 k plus 1, that's the expected value of x at time k plus 1 given all the information up to and including time k plus 1, is the predicted state x hat k plus 1k, the prior mean, plus wk plus 1, the gain multiplying nu. The term nu now stands for innovation, that's the new information, or, as we have seen it before, the measurement residual. Both terms are in common use, but it is useful to interpret it as innovation because this is the real quantity that contains the new information. So this is zk plus 1 minus z hat k plus 1k, denoted either as nu k plus 1 or as z tilde k plus 1k. Now, in view of this, S being the innovation of the predicted measurement, being the covariance of the predicted measurement, it is always, or it is also the covariance of the innovation. So we have now a new name for S, the innovation covariance. Finally, we are now in a position to calculate the updated covariance of the state at k plus 1, the covariance associated with the new estimate that we have here, x hat k plus 1, k plus 1. This will be p k plus 1, k plus 1, which is p k plus 1 k, that's the prediction covariance, minus the ph prime is either the pxz, S inverse is the PZZ inverse, HP is the PZX. So we have now one form of this. We can write it in a shorter form by factoring out pk plus 1k to the right and observing that pk plus 1k, hk plus 1 inverse, sk plus 1 inverse is w. So it's I minus wh times p prediction. There are two forms, both are algebraically representing the same thing. However, since the last one does not look symmetric, we have a compact form in symmetric fashion, that pk plus 1 k plus 1 is pk plus 1 k minus w s w transpose. So, again, this is a third algebraically equivalent form, even though numerically there are different reasons that one is superior to another, as we'll see later. So this equation 12, which was the state update equation, has a counterpart for the covariance equation 15, the covariance update equation. There is a remarkable similarity between the state update equation 12 in this subsection and the recursive least squares equation 342-15. Similarly, the covariance update equation right here is analogous to 342-11 in the recursive least squares. There is a small difference in the least squares case. The prediction 2k plus 1 from k is the same as the previous updated value at k, and this is a consequence from the fact that the least squares formulation deals with the constant parameter, which means your current estimate is the same as any prediction to a future time. Unlike in the dynamic case where the true state evolves, therefore there will be a change the state undergoes, which was not the case with the parameter that we were estimating in the static least squares problem. So there was no evolution in time. Now we do have evolution in time, and this is why the Kalman filter is a major step forward in using the same technique to a much more general situation than what the least squares was capable of. Now, using the matrix inversion lemma, one can write a recursion for the inverse covariance. We obtain the recursion for the covariance, and the recursion for the inverse covariance said that the information matrix at k plus 1 given data up to and including k plus 1 is the information matrix at k plus 1 given data up to k only, plus h prime r inverse h, or at time k plus 1. And this again says this is the additivity of information, because that's the past information, this is the new information. There is a so-called information matrix form which is covered in the text in chapter 7, which deals with this. In some cases it is advantageous. One more comment about the filter gain, the wk plus 1, which was expressed in terms of as a pk plus 1 k, hk plus 1 prime, sk plus 1 inverse, is really the same thing as pk plus 1 given k plus 1, hk plus 1 prime, r k plus 1 inverse. So, if you have here a prediction, here you have the S. You have here an updated covariance, you have here an R. two equations are again algebraically equivalent. There's one more interesting form for the covariance update equation. In the covariance update equation that we have up to now, it was implicitly assumed that the gain of the filter in the state update equation is the optimal gain as calculated using the equations we derived. What if you don't use an optimal gain? There is an answer to this question, and this is given by the so-called Joseph form covariance update. The updated state covariance is really not covariance, it's mean square error, because now it's not optimum, but it's still a valid quantity, is I minus wk plus 1 hk plus 1 times pk plus 1k. So here's the prediction covariance multiplied on the left by I minus WH, on the right by I minus WH transpose, plus WR W transpose. What's not so good about this equation, this is more expensive, it's quite a bit more multiplications, but it is less sensitive to round-off errors. It will never lead to negative eigenvalues because what you have is I minus WH again multiplied with its transpose here. You will never get a negative number for it on the diagonal, which unfortunately can happen due to round-off errors if you use one of the previous forms of the covariance update. There are more sophisticated techniques that reduce the sensitivity to round-off errors that are discussed in Chapter 7. So the main role of this is really not just to have a less sensitive expression or less sensitive recursion to round-off errors, but it can be used to evaluate the sensitivity of the filter to an incorrect gain. What is the quality of the estimates measured by a mean square error matrix coming out of the filter when I use an arbitrary gain? That is the main role of this Joseph form. It does allow quantitative evaluation of the entire algorithm sensitivity to something suboptimal, like a wrong gain. Now, we can always use a little bit of intuitive interpretation of the gain. The optimal filter gain, if we look at equation 52311, in a simplistic scalar way of looking at it, is seen to be proportional to the state prediction variance, that's the p k plus 1 given k, and inversely proportional to the innovation variance, that's the s k plus 1. So the gain will be large if the state prediction is inaccurate, large variance in the numerator, and the measurement is accurate, has a relatively small variance in the denominator. The opposite situation happens. The gain is small if the state prediction is accurate, has a small variance, the numerator is small, and the measurement is inaccurate, has a large variance, the denominator is large. So you can see a large gain means you will rely on the measurement because the past information is inaccurate. A small gain means you will rely less on the measurement because the past information is quite reliable and you don't want to give too much weight to the new measurement. A large gain indicates a rapid response to the measurement in updating the state. A small gain yields a slower response to the measurement. In the frequency domain, it can be shown that these properties correspond to high bandwidth. High gain is high bandwidth, low gain is a low bandwidth filter, because as we have seen in the first chapter, you can calculate the transfer function, and for various values of the gain, you can calculate the bandwidth. Now, A filter whose optimal gain is high will yield less noise reduction, as one would expect from a filter with a higher bandwidth. And we'll see this quantitatively in the next chapter, chapter 6. It's also important to point out that we had equations 5239 and 15 that provide filter calculated covariances, which are really exact, but only the modeling assumptions used in the filter derivation hold. You got the exact state model, exact measurement model, and the correct noise covariances, and the noises have the statistical properties as we assume, zero mean white and similar assumption on the initial state. In practice, this is not going to happen always, and the validity of these filter calculated estimation accuracies should be tested, and that we'll discuss later in this section. So you have a design based on a model, but the truth is not necessarily identical to the model. So if you cannot come up with a better model, you would like to see how good your model is, which means you will exercise your model on the truth, and you'll evaluate the results, and you will look whether the results coming out from the filter confirm the validity of your model. That's a major engineering job, that everything we are doing is based on a model, but it's not guaranteed that our models are perfect. So even if they are not perfect, we would like to know how good they are, whether we can trust them. So it's good at this point to get a bird's eye view of the algorithm we just derived, and we'll provide to this end an overview. Under the Gaussian assumption for the initial state or the initial error and all the noises entering into the system, the Kalman filter is the optimal minimum mean square error state estimator. If these random variables are not Gaussian, one has only their first two moments, then, exactly as it was discussed in section 3.3, the Kalman filter algorithm is the best linear state estimator. In other words, is the linear minimum mean square error state estimator. So it's very important to know, if things are not Gaussian, we are doing the best within the limitations of a linear algorithm, which in most cases is satisfactory. We'll see in a moment a flow chart that describes the filter in two notations. The entire past at time k or stage k is summarized by a sufficient statistic. So it's enough for us to show one cycle because the previous time is summarized. The data up to the previous time are all summarized by a state estimate and associated covariance. Here is the chart. We have four columns. On the left hand side, we have the evolution of the system, the true state. We start with state at tk, that's denoted by xk. It undergoes a transition to tk plus 1. The noise comes into the system. This is the unpredictable part of the evolution. So the new state xk plus 1 is fkxk. There is a gk uk, a known uk that enters here, plus this unknown part, the process noise. Once the xk plus 1 has been realized, the measurement at tk plus 1, that's zk plus 1, will be hk plus 1, xk plus 1, plus wk plus 1, which is the measurement noise. So there's one more uncertainty coming in. And we don't have access to v, we don't have access to w, we have access to z. We also have access to u, which means the only unknown part in the dynamic equation is v and not u. Again, in the real world, it's not clear whether v is zero mean or non-zero mean. whether it is white or not white. We have to make some assumptions, and then we'll develop the tools to verify those assumptions. This U can be a control in control systems, or it can be sensor motion or any other known input. The state estimation starts from the estimate at tk, that's x hat kk, for which we calculate a one-step prediction. X hat k plus 1k is fk, x hat kk plus gk uk. We are using as a filter. We have access to the known input, that's why it's called known. Once the predicted state is calculated, we can go and calculate the predicted measurement. Zk plus 1k is hk plus 1, x hat k plus 1k. Now we obtain the actual measurement, subtract from it the predicted measurement, so new k plus 1, the residual or innovation, is the actual measurement, zk plus 1 minus our best prediction for it. And now we are in a position to calculate the updated state estimate as a linear combination of the predicted state and the innovation. So x hat k plus 1, given k plus 1, is x hat k plus 1k plus wk plus 1, new k plus 1. What is still needed is the w. That is the weighting matrix or the filter gain, which is calculated on the side and comes from the fourth column, state covariance computation, starting from the covariance of the state at tk, that's pkk, from which we can obtain the state prediction covariance or the one-step prediction covariance for the state pk plus 1 given k is fk, pkk, fk prime plus qk. Here is the process noise uncertainty, quantified by this covariance matrix qk. The innovation covariance sk plus 1, we justified the designation for it now, or the measurement residual covariance, is rk plus 1 plus hk plus 1, pk plus 1k, hk plus 1 prime. And the filter gain is this ratio of the, again, in a matrix form, we cannot say ratio, but it's the pk plus 1k, hk prime, sk plus 1 inverse. And all those intuitive interpretations were made on this particular equation, ratio of the prediction covariance to the innovation covariance. That's state prediction covariance. So this W goes for the state estimation, and we have one more calculation. How good is the updated state? How good is the new estimate? Pk plus 1k plus 1 is the pk plus 1k, the prediction, minus wk plus 1, sk plus 1, wk plus 1 prime. So what this does is completes one cycle of the filter. And you can see the second chart with a single argument notation. It's in the text. Some people prefer that notation. Now, let's summarize again the statistical assumptions of the Kalman filter. This is one of the most important things to know the validity of any theoretical result. There is a set of mathematical assumptions that have been made, namely, the initial state x0 has a known conditional mean x hat 0, 0, with the condition being the prior information and the covariance p0, 0. Then the process noise and measurement noise sequences are zero mean white with known covariance matrices. EVK is 0, EVK Vj transpose is QK delta sub Kj. Again, this is a Kronecker delta, 0 or 1. If K different than J is 0, K equal to J, that's a 1. The expected value of the measurement noise, EWK is 0. And the expected value of WK, WJ prime, that's the autocovariance of the measurement noise sequence, is RK delta Kj. So the covariance is RK. And these three sources, X0, sequence VK, sequence WK, are mutually uncorrelated. and that's summarized in these three equations. Then, the property that we already used in the derivation was that the expected value of the process noise, V at time k, given Z super k, is the unconditional expectation. So this conditional expectation is the same as the unconditional expectation, which is 0. And again, the reason is Zk contains only Wk's, or W's up to time k, and previous V's up to time k minus 1. Similarly, E of Wk given Z super k minus 1, this conditional mean of Wk is the unconditional mean, and that's 0. Again, we also assume F, G, and H, and actually Q and R, are all known quantities. You might think that this algorithm is very limited in scope because it made a lot of assumptions and we emphasize those assumptions. It turns out that most of these assumptions can be relaxed. White process noise can be relaxed, doesn't have to be white. White measurement noise, again, can be relaxed, doesn't have to be white. The two sequences, process and measurement noise, their uncorrelatedness requirement can be relaxed. Again, these are more general versions, and all these more general situations can be modified such that you have a slightly different system, mathematical model for the system, which now is A, equivalent to the one with, say, not white process noise or not white measurement noise and so on, and it does fall into the standard problem formulation. So you modify the mathematical formulation, the model, so it can be solved by exactly the same algorithm. Just a few words about how this is done. If you have autocorrelated or colored process noise, you model it as the output of a subsystem driven by white noise. It has to be pre-whitened. By appending this subsystem to the original system, you got a larger system, but now it is all driven by white noise, so we are in the standard case. If you have autocorrelated process noise, you can augment the state vector to incorporate so for the autocorrelated process noise, we augment the state vector and incorporate this pre-whitening system. The situation where there is correlation between the two noise sequences can be handled, and again the two noise sequences can be decorrelated, and when you have autocorrelated measurement noise, again there is a smart way of modifying the measurement equation. This can be handled even without augmenting the state. Some of the other topics, discrete time smoothing and continuous time state estimation, are presented in chapters 8 and 9, which due to time limitations for this course we are not going to cover. Now, we have seen the covariance equations. There was a state prediction covariance and a state update, the update of the state covariance. So the two steps, covariance prediction and covariance update, can be lumped into a single equation as follows. First, would like to mention that the covariance equation, the static minimum mean square error estimation problem, are independent of the measurements. Consequently, the covariance equation for the state estimation problem in a linear dynamic system, as we derived before, are also data independent and can be iterated forward offline. we can write the following recursion for the one-step prediction covariance. Pk plus 1k in terms of pkk minus 1. This equation, which says that instead of, it's more convenient to write a recursion of one prediction covariance and versus the previous, or in terms of the previous prediction covariance, than an updated covariance in terms of the previous updated covariance. Because this equation is well known as the Riccati equation, and this says that pk plus 1k is fk pk k minus 1 minus pk k minus 1 hk prime times hph plus r inverse, remember this is the s, hp f transpose plus q. So this is a prediction equation, ff transpose, this is an update equation, so we lump the update into the prediction and we go one step up in both arguments. Now, this is known as the discrete time or difference matrix Riccati equation, or just Riccati equation. It's nonlinear. You can see a p here minus a p, but that's multiplied by another p and divided by another p. So clearly it is a nonlinear equation. This has been studied by Riccati, obviously, for a time invariant system. Turns out we have a following very strong result. It will converge to a finite steady state covariance under two conditions. The pair FH, that's the system transition matrix, this is the measurement matrix, is completely observable if, so it converges to a finite steady state. There is no result about uniqueness or the exact nature of the solution, but there is a finite that's bounded from above clearly. If the pair FC, and by decomposing Q into CC prime, C is a Cholesky factor. It's like a square root of Q. So F and the square root of Q in the Cholesky factorization sense is completely controllable, then the steady state covariance is unique and positive definite. We said it's bounded from above, now it's bounded from below. It cannot have zero eigenvalues. Has finite eigenvalues from result 1. Now, second condition says A, it is unique, B, no zero eigenvalues. And this whole thing is now independent of the initial covariance. The steady state covariance is the solution of the algebraic matrix Riccati equation, or just algebraic Riccati equation, which is what we had before, with all the time arguments removed. Remember, we are talking about a time invariant system. F is time invariant, Q, H, and R are all time invariant. And this is the prediction, one-step prediction covariance, this P here. If we have a fixed solution to the covariance, we also have a steady state gain, because the gain is given directly in terms of those, of this covariance and the Q and the R. So what we have now would be a steady state gain for the Kalman filter. So the filter, the dynamic system which represents the filter, becomes also time invariant. Couple of interpretations are useful for these results. What does the observability condition really tell us? It guarantees a steady flow of information about each state component. This will prevent the uncertainty from becoming unbounded. Remember, when you have the state prediction equation, you always add the process noise to the uncertainty. What you have now is also a measurement equation that subtracts it. The very early chapter 1 description, graphical description of a scalar case in terms of the covariances, it goes up in the prediction, it comes down in the update, up and down. But there was no result about what happens in the longer run. Now we know. the conditions under which it goes to a constant value. There will be one constant value for the prediction covariance, another constant value for the updated state covariance, and another constant value for the filter gain. So the observability conditions yields the existence of a steady state solution which can be either positive definite or positive semi-definite, guaranteed to have finite, positive or non-negative eigenvalues. So it's bounded from above, cannot be negative unless there are numerical errors or coding errors in the evaluation. Obviously that's out of question right now in the theory. So bounded from above means either positive or non-negative eigenvalues. Now the second condition, controllability, states that the process noise enters into each state component and prevents the covariance of the state from converging to zero, or for any state component. For no state component can you have a zero eigenvalue now. So that is the root of the positive definiteness result. It's unique, and the eigenvalues are all greater than zero from condition 2 and less than infinity or finite from condition 1. So this is the meaning of controllability. Noise enters into each state component. So in the case that we have a finite steady state for the covariance, the error becomes a stationary process in the mean square sense. This is equivalent to filter stability. Bounded input, bounded output. That is the essence. We have mean square bounded inputs, the noises, and the estimation error coming out of the filter is mean square bounded. Will become stationary. Now, very important, for the filter to be stable, to have a finite covariance for the error, it will not require the dynamic system to be stable. Nowhere is a stability requirement for the dynamic system, which the F matrix does not have to be stable. But as indicated above, observability still does not guarantee uniqueness. If you have the system observable but it is not controllable from the process noise, the steady state solution might depend on the initial covariance, but the existence, the finiteness of the solution is the key. So that's bounded from above. Now, why this is important? All the state models used in tracking are unstable. They have an integration. What happens to velocity in continuous time? It's integrated in the position. That's a zero eigenvalue in continuous time, a unity eigenvalue in discrete time. That is not stable. Stability would mean bounded input, bounded output, and such a condition is not satisfied by an integrator. So the original dynamic system is not stable. Has a transfer function with the pole at the origin in continuous time or at 1 in discrete time, but the filter is guaranteed to be stable. Few more remarks. If the state covariance is positive semi-definite, what does that mean? Has zero eigenvalues. Then the filter believes it has a perfectly accurate estimate or estimates for some of the state components or some linear combinations of them. What happens when you have a perfect estimate? What do you do with the gain? Down to zero. The gain will be zero for those state components. This is a very undesirable feature because in the real world you cannot have perfect estimates. So you never want your filter, state estimation filter, with a gain that has even a component of it down to zero, has gone to zero. It's undesirable. In view of this, in many applications where there is no physical process noise, we still use an artificial process noise or pseudo noise. We assume a matrix Q in the filter model such that our second condition, that is the controllability from the process noise, is satisfied. This is important because this prevents the filter from shutting down. Gain going to 0 means the filter has shut down, and you don't want that, because you know that you are bound to have made some errors, either modeling errors or some numerical errors, and therefore you want to be able to continue using new data. You don't want the filter to shut down. One more final comment on the Riccati equation and the Camera lower bound. We have seen the lower bound on the minimum achievable covariance in state estimation will be given by the posterior Camera lower bound, which was presented for random parameters. So this is applicable for state estimation. In the linear Gaussian case, it can be shown that the Riccati equation solution provides that lower bound. But Gaussian case means everything is linear and Gaussian, and the estimator, the optimal estimator, is linear. So we already have done the best. So whatever we are doing equals the best. So the actual solution coming out of the Riccati equation is the Camera lower bound. But in the more general non-Gaussian case, the solution of the Riccati equation is the covariance matrix, really is a mean square error matrix associated with the best linear estimate. But, as we discussed earlier, a non-linear estimator can provide better estimates with covariance smaller than what the Riccati equation provides. So, if it's a non-Gaussian problem, you got the first two moments of all the random variables, use the Riccati equation, you come up with a covariance matrix or a mean square error matrix, you can achieve it. But this doesn't mean that's the limit. The bound is somewhere below it. But if you have the same moments and everybody is Gaussian, the bound is exactly what the Riccati equation gives you. The practical problems with nonlinear estimators are we usually don't have them. Cannot calculate an optimal nonlinear estimator, except in the Gaussian case it's obvious, it's linear, but if it's non-Gaussian it's very hard to calculate for a dynamic system.